to share his screen. Perfect.
Okay.
So let's get started.
And thank you all for being here. What I'm going to do is just run through the introduction and then hand over to Fabrizio and Cristiano. So what I'm basically going to do is just illustrate what new things we're doing. What I've done is put them up in bullet point format first and then elaborate over the next few slides. In a sense, they're all connected, but it's a good idea to sort of separate them at this point. So these are what we would say were the key differences between what we're doing and, let's just say, traditional ideas. So we're not connecting up the prior to the model. So if we have a theta space, the prior won't actually end up depending upon the F, the data model. Many Bayesian assessment ideas typically rely solely on notions of log score, Shannon information, callback-Leibler divergence. And one of the ideas, or the key idea for us, is that we're going beyond that. So we're actually moving out of that these sort of restrictive items. As a consequence, we do end up having a more flexibility. So the flexibility is it's not something you would say, okay, well, that doesn't define something uniquely. What it does allow us to do is to introduce shapes. So we can use the flexibility gain to construct priors for which we have shape constraints, such as log concave, convex, unimodal, monotone, and properness as well. So probably that's one of the key ideas, is that we can move away from the traditional improper prior. The notion of information is still important to us, obviously. The key difference being that we're now using information directly onto the prior, rather than this common theme, which is that information is often looked at as a difference between prior and posterior. So we're not using information as a sort of information gain between prior and posterior. It's a direct one onto the prior. So I guess that's why, if you're thinking ahead, that's why we lose the connection to the model. So we're not actually invoking the posterior to do this. Okay, so I'm going to run through each of those and elaborate on them a little bit more, not necessarily in the order in which I've just written them. So, as I was saying, the key ideas that traditionally are used with Bayesian assessment of procedures involve the three items, I'd say: the differential information, callback-Leibler, and score, log score. The Shannon information here is important. This is one of the key items. So, for example, if you're looking at the expected callback-Leibler divergence between the prior and the posterior, the I is important. This information is important. It can be written in this sort of Jensen inequality type. So it's positive because this is just a Jensen inequality. So the idea of trying to maximize this divergence is effectively equivalent to trying to maximize this Jensen inequality. And so don't want to comment further on whether that makes sense or not, but the point is that if you've got this information and the integral P log P, and you'd say, well, okay, let's start from this position here. You'd say, well, I'd much rather directly try and minimize that IP as a sort of objective, non-informative prior, then go through this maximizing the Jensen inequality involving the Shannon information. But of course, as we all know, that's not possible because there's no variational calculus that works in this particular case. It can be made to work if you're willing to add extra terms to IP. So if you take the IP and you start adding terms to it, so this would be sort of maximum entropy ideas, that's not where we're going. But if you're willing to add terms to this IP, then you can. And in a way, that's where we're going. The extra flexibility is moving to give us something slightly different to this IP on its own, which allows us to use variational techniques. Again, trying to put all things together, one of the key connections that looms large over all of this work is this connection between divergence information and score. So the three that we've just been looking at, log score, Shannon information, and Kullback-Leibler divergence, are connected in this way. And they have become almost uniquely used in, as I said, in Bayesian assessments. But there's a whole family of these kind of setups where you do have divergence information and score, which are not restricted to the one we've described here. So we're, in another sense, we're looking, I mean, as I said, they're all the same at the end of the day, but we're looking for more sophisticated divergences and score functions. So we're just looking for different forms for D, I, and S here, going beyond the traditional ones that are used. So where we actually came at this from is, you start at one place and then gradually you meander and you realize that you're actually connecting up a number of things, and then you can start fitting things together. So we actually started off by really just trying to elaborate on the score. So one of us was playing around with score functions and looking at papers by people like Matt Parry and so on. And this is known as the Heaver-Enan score. So basically what we're doing is we're just combining the log score with a more sophisticated score, which involves derivatives. It looks at first sight a bit strange looking, but really it's just involved first and second derivatives of log Q. Okay, so it's not really as strange as it first might seem. The corresponding, there's also these D and I associated with it, which satisfy the equation on the previous slide. So the information is known as Fisher information, and the divergence is the Fisher distance. So these are the two expressions here. So those three are linked in the same way that the Shannon information, Kullback-Leibler, and log score are connected as well. So in a sense, we're not really going extraordinarily out of traditional thinking here. We're just extending what's already there. So it's these derivatives which actually give us the flexibility now. It's having this, and we'll see where that actually comes in later. So as I said, we started off, our first thinking about this was well, if we're trying to be objective, why would we think anything other than setting the score function to be a constant? The actual constant doesn't matter. That's because the normalizing constant for the density soaks up any arbitrary constant we make SQ to be. So you can set it at 0. That's not a problem. So the first thinking was, well, objective could be just the idea that you're setting the score to be 0 for all the theta, for each theta value. as we discovered later, that also has the merit of minimizing the information content. And given this extra flexibility, we now have variational calculus to use, and we do end up having minimum. So by adding this extra piece of information, if you like, we can now actually do a proper minimization. So we get a class of prior, which is actually in the heading, because we have we get constants of integration. So as we go back to solve the equation, we obviously get some constants we need to put in, and yet we use those. It's not that we're using those in a subjective way. Those can be used to invoke certain shape constraints and ensure properness. So looking at it from an information perspective, so we can, if we set the score to be 0, we get an immediate equation. So that would be fairly easy to see. So that's the SQ we have up at the top of the page there. If we set that to 0, we get an immediate equation to solve, or a second order differential equation to solve. If we look at it from the information point of view, then we're literally just adding the Fisher information in a weighted form to the Shannon information. And by virtue of doing that, we do now have Euler-Lagrange equations which we can solve and obtain a minimum. So if we look at the second derivative matrix here, we can find that it's positive definite. And so those give us the conditions for being able to solve the problem. And actually, if we then get the Euler-Lagrange equations, we get exactly the same equation as we did with the setting the score function to be 0. So as I said at the beginning, the lack of connection to the model is because we're looking at information into P directly. We're not going through this route of looking at the information difference between prior and posterior at all. It's not clear whether the idea that it depends on the model for various reasons. Historically, it's been connected to the model for invariance reasons, and then realizing you can't minimize the Shannon information, and therefore looking at difference in information, even though it's difficult mathematically. I guess there's some maths that can be done. So historically, you wonder whether this connection to the model is out of necessity rather than out of any obvious fundamental reason. We did feel the need to sort of elaborate a bit on this. So this is something I've been trying to write down for years. The idea that, as a sort of coming at things from a Bayes non-parametric point of view, to me the correct prior, if you like, is always the one that you invoke on the density functions rather than on the parameter. So if you look at this, then, the F is obviously going to be chosen for fitting purposes. If you're generating random densities, you'd always like one of those in the support of those densities to be one that you think is going to provide a good fit. And if you're trying to invoke subjective ideas, then clearly you want to introduce or have the model and start directing the densities, these random densities in certain regions, so that's where you believe the density is most likely to be. Without that, it just seems like, well, it's almost like saying, well, I can't think of any good reason why I'd want to connect the P to the F here. In the sense that we're not really trying to guide those random densities over any particular region of the density space, being the chief reason here. So let me just, it's clear that invariance or lack of is going to be part of the discussion. this would just be a sort of defense up front, although there are other things that can be said about it. The Shannon information is known to be not to be invariant under reparameterization. So you can change the order just of the equality just by doing a reparameterization. But the point is, it's widely used because in many contexts, the advantage of being able to use it without spending the next part of the research agenda just reparameterize everything just for the will of it. Its use outweighs this issue. And I'm not saying that's necessarily our argument about the lack of invariance. Only to say that many widely used procedures lack invariant properties, many, including things like classical confidence intervals and even Bayes estimates. So it can only be argued that their use overcomes that lack of invariance issue. Okay, so in summary, for me at least, so we solve the score function to be 0. So there should be a theta in there. It's SQ theta. So for every theta, the score value is 0. And that leads to this particular equation. And then it also is derivable through the variational calculus by attempting to minimize this notion of the combined information of Shannon information and the Fisher information. So that's what allows us to directly attack information in the prior itself without having to go through some alternative route, namely maximizing some difference in information between prior and posterior. Okay, so for me, I'm ready to hand over to Fabrizio at this point.
Yes, thanks, Stephen. Let me share my screen. Okay. Sorry. Can everyone see?
Yes.
Okay, so first of all, I want to thank Michele for selecting our paper as discussion paper for Bayesian analysis. As Stephen said, we really appreciate very much. Thanks to all the people that contributed to the discussion. Really liked most of the point made by the discussants. And finally, thanks for all the people that are attending today the webinar. So at the end of his talk, Stephen displayed the differential equations. This differential equation is the result of setting the scoring rule equal to 0. We said that our prior fulfill this principle. So we believe that objectivity is about setting the scoring rule equal to a constant. So as Stephen said, the constant is not important, and 0 is what we can start from. So if we look at this differential equation, it depends on a parameter w. If we fix w equal to 1 and we work the differential equation, we obtain the equation that is at the bottom of the slide in equation 1. So a class of solutions of this differential equation is the one that is proportional to the exponential of minus u theta. U theta itself satisfies a first order differential equation, which is u prime theta equal to plus minus, so we can choose the sign, square root c exponential of u theta minus 1 plus u theta. Here, in order to get a specific solution, we have to choose a constant c and set, as usual in differential equation, an initial condition u0. And so if we want a specific solution, we need to set these two parameters, c and u0. And what we are going to do is to show some examples on how to set c, u0 with different parameter space. And in particular, we see what kind of properties we can get for our prior. So in general, a solution of this differential equation is not easy to find, but it's not a problem because we can get solution numerically, and in particular we can use a Taylor expansion. This Taylor expansion is not difficult because the derivatives can be expressed in terms of the function u. For instance, if you look at the differential equation in equation 2, you can see that u prime depends on u. If we iterate this differential equation in terms of derivative, we can get similar expressions. And so it is very easy to implement. However, I want to show to you a couple of examples where the solutions are actually explicit. In particular, consider the parameter space minus mm. And for the moment, let's fix w equal to 1. It is the weight that we saw at the beginning of the slides. So, for instance, we set c equal to 0. For a solution to exist, we need to have 1 plus u theta negative, otherwise the argument of square root would be negative. So if we choose the positive sign in the square root, it is quite straightforward to see that a choice for 1 plus u theta could be minus 1 over 2 theta minus mu square for some mu. So the resulting prior is proportional to the exponential of 1 over 2 theta minus mu to the square. This prior can be normalized, and so we get a proper density. This is quite an epic case because we are able also to provide a solution when we consider a generic weight. And the solution doesn't change too much, so we have this w in the argument of the exponential that multiplies theta minus mu to the square. So just to show the behavior of this prior, if we select m equal to and we plot the prior for different values of w, and we set the initial condition u0 equal to 0, we can see that the shape of the prior changes with the weight. In particular, if the weight increases, the tails become heavier. Cristiano will show more on this point, because actually, as a general rule, if you play with this weight, you can play with the tails. But Cristiano will tell more on this point to answer one of the queries of the discussants. So another obvious solution. So now, if we consider instead of minus mm a generic parameter space, we can actually recover the flat prior if we set c equal to and u0 equals 0. Now, what we are going to do is to show how to find the class of priors for different parameter spaces with specific properties. And in particular, we see how to set c and u0 in order to get such priors. The cases that we will consider are the space 0, 1, the space 0 plus infinity, and the last one I will not tell more, simply because you can get priors for minus infinity plus infinity by using by symmetrizing the priors obtained for the previous case. So let's see the case where we consider the interval 0, 1. So I recall that the prior is proportional to the exponential of minus u. Here we want to obtain symmetric priors such that in the extremes of the interval, the prior is 0. So a way to obtain such prior is by setting the constant c equal to set the initial condition, now not in 0, but in 1/2, but we know that for differential equation, this doesn't matter too much. So the initial condition positive, and now we select the differential equation with a positive sign for theta greater than 1/2, and the differential equation with a negative sign for theta less than 1/2. You can spot immediately that there is a discontinuity in the derivative of u at theta equal 1/2. This just for the change of sign. Now, if we display the solutions of this differential equation, so if we display the shape of u for different initial conditions, in panel A, we have the solution of u when the initial condition is 1.1, and in panel B when it is slightly more, which is 1.14. What we note is that when we increase this value, we approach infinity faster. The panel C is the prior, so the exponential of minus u normalized for the case of panel B. We can appreciate the discontinuity in 1/2. If we want to mimic the behavior of Jeffreys prior, you just have to set u equal minus u in the above, in the previous procedure. In the case 0 plus infinity, we want to ask a little bit more in terms of properties, because in the previous case we asked symmetry basically and a behavior at the extreme. Here we would like to obtain a prior that is convex and decreasing. This because maybe many standard objective priors have this kind of properties. And so if we want a prior that is decreasing, we have to ask that the derivative of the priors is negative. Now, this case, for the way that the prior is defined as the exponential of minus u, p prime is equal to minus u prime p. This means that in order to achieve that the prior is decreasing, we need to ask that u prime is positive. And therefore, we take the differential equation with the positive sign, and for solution to exist, we need at least c that is 2. We select the extremal value, and we see what we have to select as u0 in order to get a prior that is convex. We know that convexity can be achieved when the second derivative is positive. And now, if we iterate the first derivative, we obtain a relation of the second derivative, which is the prior times this difference of u prime to the square minus the second derivative. And therefore, the terms in bracket must be positive. And this translates in the inequality that I'm pointing here. Now, details are in the paper of how we solve this, but this led to a value of u0 that is approximately 1.31. Now, a nice result that we have in the paper is that if the prior in 0 is finite, we are able to prove that our prior is proper. The proof is in the paper and is a nice application of the Gromwall's lemma. Now, to display this prior, we can look at panel A in this plot. Now, when we consider the case minus infinity plus infinity, we can symmetrize the prior that we just found for the case 0 plus infinity. Now, if we do this, we are going to have a discontinuity in 0. We can do this, but if we don't like the discontinuity, we can try to smooth the prior in that point. In the paper, we give details how to do this, and the resulting prior is the one that is in panel B. In panel B, I'm just displaying the positive half of the prior, so not the void prior. So a nice property of our class of prior is that you can obtain prior that are proper, and this is a good property because there are scenarios where objective priors are notoriously challenging. For instance, in mixture model, but also, for instance, when we compute base factors in model comparison. So I will quickly show an example of mixture models. So here, just to fix the notation, we have a mixture model with k components. The weights are these omega j's, and we have a mixture of normal distributions, which means mu j's and variances sigma j squares. And so we know that even in scenarios where k is known, objective priors may be difficult to derive. We have many examples. For instance, Jeffreys priors can be only obtained under specific conditions. There is a nice paper of Clara and Cristiano, a recent paper, that discuss various scenarios about Jeffreys priors for mixture models. Another problem is that if the unknown parameters are the means of the variances, if you use Jeffreys prior, these may lead to improper posteriors in most of the cases. And so, since the prior that we are proposing is proper, therefore the posterior is proper, and this allows us to make inference for the parameters. And if we look at the simple example of a mixture model with 3 components, here we selected the weights as 0.25, 0.35, and 0.40. I'm not going to list the numbers, but let's say that we selected the means in a way that are reasonably distant. In the paper, we have a simulation study for 2 scenarios, n equal 100 and n equal 250. Here we show just the case for n equal 100. As I said, we have chosen the mixture component in a way that are reasonably distant, so we don't have to impose any constraint to overcome identifiability. On the parameters we select our priors, and now I'm going to show the plots of the traces and some histograms, which will show a clear convergence of the posterior chains and let's say a reasonable inferential results. So here are the plots. So the chains are not so bad, but let's see the histogram that maybe are a little bit more clear. So in panel A and C, we have the histogram for the first 2 variances. And in panel B and D, we have the histograms for the first 2 weights. In A, the true value is 0.5, so they are not so bad. And in C, the true value is 0.1. For the weights, in panel B, the true value is 0.25, and in panel D is 0.35. So to conclude this talk, we introduced a novel class of priors through scoring rules. Here, the idea is that we do not favor any parameter values in terms of loss. I remind you that scoring rules can be seen as a loss function. In the paper, and Stephen also commented about this, we show that this class of priors can be alternatively derived by minimizing a notion of disformation, which incorporate both global and local information. The nice thing is that the two approaches agree, and they lead to formulate the problem as the solution of the same differential equation, and we illustrated the method in different parameter spaces. And the nice point of our class of priors is that you can obtain proper priors, which makes the inference possible in scenarios where notoriously objective priors have problems. And so thank you, and now the floor is for the discussants.
Thank you, Fabrizio. Thank you, Stephen, for the presentation of your framework. So when we decided about selecting this paper for discussion in Bayesian analysis, the editorial board realized that it is a thought-provoking paper, so we asked multiple discussants to provide their perspective, and in particular discussants mainly from the objective-based community and other discussants that have been working with scoring rules in the Bayesian literature. So we start first with Dimitris Fuskakis. So if Dimitri could show his
yes.
Perfect, great, thanks.
Give me just a second. Let me start sharing my screen. Okay. Is this okay for everybody?
Perfect. Could you put it on full screen?
Yes, let me do it full screen. Let me see what's going on here. Just a second. I think it's this. Okay, now it's better, right?
Perfect. Thanks.
Right. So thank you so much, Michele. It's really a pleasure to be here today. Thank you so much for the discussion, for inviting me to discuss this beautiful paper. And also thank you for organizing this webinar. It's really nice to be here today and see some really good friends of mine, even virtually. I hope that soon we're going to meet in one of the conferences that we have and share some ideas. So let me start by giving a brief outline of the paper. I think that this is a very interesting paper, introducing a new class of objective priors derived from scoring rules. I really enjoy reading the paper. I really enjoying the presentation of the paper today by both Stephen and Fabrizio. As they mentioned, the aim of the paper is the definition of a new class of objective priors. First of all, these priors that are detached from the choice of the sampling distribution, and they depend only on the parameter space. And as they saw in the paper, they can be proper. The authors, they measure the quality of the prior with a proper scoring function. And as they mentioned also in their presentation, they require it to be constant. And main focus is given in uniqueness and invariance of these defined priors. And they have some nice applications on mixture models and model comparison via base factor problems. Here is an outline of my comments, and my comments are mostly focused on the model selection problem. The main reason for this choice is that I believe that the O-base community and methodology for priors started more recently, and its development and applications to various models have increased over the last few years, especially nowadays that we face with multidimensional data and many models to be compared. With my discussion today, but also written in the journal, I wish to add some further insights to the paper, resulting in future work in the area and probably some more collaborations. So let me start. I know that I don't have a lot of time with some comments. The first comment has to do with how easy it is to apply the proposed methodology in more complicated model selection problems. And since the marginal likelihood is not analytical available, how easy eventually is to derive the final base factor. The authors in section 6.2 of the paper, they consider a simple nested model comparison problem, and they make a nice comparison of the proposed prior with the intrinsic prior as is presented in a nice paper by Guido and the rest of the people in 2013. So I would like to see some more comments on the derivation of the base factor, but also what's happening in more complicated cases. I'm a big fan of variable selection problems, and this is, I think, one of the most common applications of model comparison for normal linear regression models, but also for generalized linear models. There are so many methods out there that people can use. I believe it would be great to see an application of the proposed methodology in such problems and to compare the performance of the proposed method with that of the most established Bayesian variable selection techniques. Furthermore, I remember a paper, I think it's still in archive, by Camry, I think it's Kerry Mergerson, it's Cristiano Bert and Judy Rousseau back in 2018, that they faced the variable selection problem as estimation for mixture models type of problem. So the authors, they have done a case study and application of mixture models, so probably they can see, they can use this idea in order also to see some results on variable selection as well. Also, I'm a very big fan of this paper almost 10 years ago now by Susie, Garcia Donato, Gonzalo, and Annabelle and Jim Berger, that they developed these desiderata, the criteria that have to be satisfied by objective prior distributions for Bayesian model choice. And of course, a number of these criteria is applicable only in nested model comparisons. And I believe that predictive matching is probably the most crucial aspect for objective model selection priors. So I would love to see some work on this direction. For example, even in nested cases, in nested model comparison cases, to see if some or all of these criteria are satisfied for the proposed prior. Furthermore, in this paper by Susie and the rest of the team, first the criteria for priors, all these criteria for priors, meaningful, they were set out, and then the priors satisfied them, they were derived. So probably this can be done in this paper as well, in order to select the constants that are required to be selected from this prior based on these criteria. Also, returning back to the desiderata, and if I understand correctly, the proposed priors can be local or non-local, depending again on the choice of the constants. So again, I would love, for example, to see some work on the non-local prior setup and some comparisons with the ones that Johnson and David Rosell use under specific cases. I believe that the fact that the prior is detached from the choice of the sampling distribution, it's a big advantage in some cases, and probably it's a big advantage when we have a model misspecification. And this is an area that many people have worked. Again, there is a nice paper by Rubio and Rosell in 2018. So my question here is, does model misspecification affect the selection of the true model under the proposed prior, or since the prior is detached from the choice of the sampling distribution, this problem does not arise? So I think this is a nice avenue to be explored by the authors, and probably it's a big advantage of their method. And finally, I mentioned it before, current applications of statistical models and methods often deal with high-dimensional models, especially nowadays. And we all know that the derivation of an objective prior, it's virtually impossible in such setups. So my question again here is, how possible is to apply the proposed methodology in high-dimensional models? And again, I'm going to return to the selection of the constants of integration. It would be nice to see under this type of problems how this selection affect the degree of shrinkage, for example, if the aim is to do some shrinkage on these high-dimensional models. So this is the end of my discussion. I know that I don't have a lot of time, so for once more, I would like to thank the authors for this very nice paper on a very important issue. I truly believe that the paper is a very useful addition to the literature of objective priors. So very nice work. Congratulations, Fabrizio, Cristiano, and Stephen.
Perfect. Thank you, Dimitris. The second discussion was by Gonzalo Garcia Donato and Guido Consonni.
Hello, good afternoon. Good afternoon from Spain. I don't know. Sharing my screen. Can you see the screen? Can you see the slides?
Perfect.
Okay. So I want to start saying that this is joint work with Guido Consonni from Universidad Católica in Milan. And I would like to thank the journal Bayesian Analysis for the invitation to participate in this discussion panel of this paper, and particularly to Michele. And my first word is to say that for many Bayesian practitioners to enjoy the posterior, some others have to suffer the prior, and this is a very nice example of people thinking on the prior. And I would say this is always very discussed about prior, and this paper is a clear manifestation of that this issue of the specification of the prior is a live question in the Bayesian community, and also is that it's very significant that our flagship journal, this Bayesian Analysis, is open to this type of topics, so that you even invite this to be a discussion paper. I would like to thank the author, because this is a very nice paper, a thought-provoking piece of work in the area of prior assignments. And now I will start with my discussion. It's going to be just few slides. Which are the main motivation ideas here? Is that the main idea is that current methodology for building objective prior depends on the statistical model. So the point in the authors is that as model grows, as the complexity of the model grows, then it does the difficulty in obtaining the prior. That's true. And also a point in the paper is that normally, or quite often, the objective priors are improper. So then this cannot be used to obtain, for instance, the base factor. It cannot be used in model comparisons, at least in general. And normally, assessing the posterior propriety is very difficult to be obtained. So then they set up a program in finding objective priors, which only depend on the parameter space. They don't depend on the model use. And this is very, so when I first read the paper, this is very surprising, because if you are a guy working on objectives that, okay, you cannot use the data, be careful because you cannot use the data. Okay, but at least I can use the model. That is going to be my main source of information to build the prior. So that's something that you normally like using because you can use the model. But then even in here, the authors go a step further, and they even don't allow or they don't use the model. That's a quite surprising feature in this paper. And they set up the root in fixing a constant scoring rule, and then with that they obtain their prior. And this, as was told by the author, this is a major departure from more traditional principles to formalize ignorance, where the formal structure of the model is used, and this is used to obtain the prior. So this is what they call the model-dependent prior, but that is just the traditional way of assigning priors. And part of our discussion is trying to see if this is possible. If this is possible at all to construct good or optimal priors that doesn't depend on the model. And this is several critical features of the proposed approach. First of all is that normally if you go and then read a paper about priors, if you are a practitioner and then you want to use these priors, you don't want to be that variety of possibilities. So the family of priors you were saying in the main talk, the family of priors that have a constant rule is typically very large, and in particular it always includes the uniform. So this method requires, as you were seeing, ad hoc supplementary arguments to be able to construct a particular prior. And in many cases, this is quite surprising as well, is that some of the arguments are based on the traditional objective prior, which of course, those depend on the models that is being used. Our second concern that stands for a critical feature in this approach is, does invariance matter? As it was told and is written in the paper, the method is not invariant to reparameterization. And the authors say that if invariance is a concern, which is for some of us, for me is a concern, something that is not invariant, then one can identify the preferred parameters. So for instance, the canonical parameter in the exponential family. And from there, you can go and then transform back using the standard transformation formula. But then again, you have to identify the model, and then you have to use feature of the model. So for instance, which is the canonical parameter is connected with the model you are really using. So at the end, you are in a sense using the model. So you see all these comments go into the direction that although you can have a nice proposal, but if you want to go and then to refine, to produce something that is optimal, then you have to look at the model in a sense. And then that's as Dimitris was saying, this is my favorite area of research, is prior for testing. And then I have to say that this is very appealing. This proposal is very appealing because the priors they are proposing are almost by definition they are proper. So these are very appealing for testing priors because we know we have to use proper priors. And then what we did is to assess the performance of the prior used by the authors. One of the priors that is the one that goes in the real line from minus infinity to plus infinity. And then we use in several paradigmatic simple examples in testing. And then we found we were playing around these criteria in this paper by Susie and some others. And we were playing around these ideas. And for instance, we arrived to the following conclusions that if you try, I mean, that's again because we are a model guy. But if you spot a model, then we normally identify which are common parameters and parameters that are specific for the testing. And then when we try to use this prior, the prior they are proposing in common parameters, then we came up with something that violated the predictive matching criteria, and that was worse if the parameter of if the dimensionality of the parameter was large. And also, if we went and tried to use their proposal, when we have several parameters, and then we use independence within the parameters, something that they justified that could be done, then we obtained something that was quite the undesirable behavior of the Bayes factors, something that it was not completely monotonic. So, and that's something we discussed, Guido and myself, we discussed a lot, that this was, okay, this was only with that prior. We choose from the big family of prior that they are proposing. We were choosing the one that we thought that was one of the main proposals, one of the main specific proposals in the paper. So one can imagine ways of selecting a prior within that big family, in the sense that has a much better performance and doesn't have the problems that I just described. But then what we clearly thought that will imply to go and then to dive into the model to see which things, which properties you want to have, something that even Dimitris was telling. So that brings us to the original question: is it possible to derive optimal objective priors without using the models? So I think we think is not possible. And then just using the parameter space, you cannot obtain something that is optimal. And with that, I finish my discussion. Thanks again for the invitation, Michele.
Thank you, Gonzalo, and thank you, Guido. The next discussant is Matthew Parry from University of Ontario, and I want to thank him especially because I know that it is pretty early for him right now.
No problems. Let me just quietly get my screen organized for you. Thank you very much, Michaela and Bayesian Analysis, for organizing this Zoom meeting today and reading of the paper. I have to say, actually, am I looking at my screen or?
Not yet.
I am, sorry. I had it set up to go and it seems to have disappeared inevitably. This will work here. Oh, that's the wrong one. Here we go. It's a real privilege to be asked to discuss this, but also it's a real privilege to connect with all of you at this time. So I'm really grateful that this has been organized. It's great that we can keep our community going. Here we go. So I guess I'll start off just by again saying congratulations to the authors for this really thought-provoking talk, and seeing all the discussions and all the other discussions that have been added to the paper. It's clear that it's a really interesting and going to be an important paper for many people. Well, I wrote a paper on the scoring rules in 2012 with Philip David and Stefan Lauritsen, and it was packed full of theoretical ideas, and we didn't quite know how they were going to get used. And it's been great to sort of see how much has been done with local scoring rules, not derived from our papers necessarily, but just in general in the last decade or so. So that's sort of a preamble to say that I'm probably going to take a slightly theoretical direction in my talk today. And so I want to talk a little bit about how these objective priors have been characterized or constructed in the paper. In sections 2 and 3 in the paper, the construction is a solution to the scoring rule being equal to a constant, sort of equation 1 here. And then in section 4, the priors are seen to be solutions to Euler-Lagrange equations for a particular functional form of L. So L here, I've chosen W to be 1, I think, but it's obviously that can be inserted there at any point. And so they look to be quite distinct, but they actually are linked in the paper. But what I want to talk about today is that this linkage can actually be broken, and maybe we could actually generalize these concepts quite usefully. And in so doing, we'll also probably see the connection which exists between information, which Stephen talked about, and scoring rules. So it's not, I feel like it's not quite as mysterious as it may be to some. So the first comment really is that the way that we construct them in sections 2 and 3, I will argue, can really be thought of as a generalized uniform distribution. And this is an analogy with the generalized exponential distributions that Grunwald and David proposed in 2004. And those are solutions to the equation I've put on the screen here. I won't say it out loud, but you can see it's a scoring rule being set equal to a particular combination, which involves constants, but also functions of theta as well. And this form is not chosen randomly, but it's chosen because if theta in this case were actual data, so actually normally we think of scoring rules for observations given some model, then if theta was data, then in fact the associated estimating equations would be separable. So it has a nice analytical form in this way. So in this way, if we just get rid of the theta dependence, then we just revert back to the characterization that the scoring rule is a constant. And so that's why I'm sort of terming that a generalized uniform distribution. And it seems to me that that would be a reasonable starting point in that light for those types of objective priors. Now, what Stephen and co-authors have pointed out in the talks today was that, of course, S being a constant is actually generally not going to give you anything interesting, or certainly nothing that's actually normalizable. And what they've highlighted in their paper is that the scoring rules they have been using actually allow you to come up with proper priors and non-trivial priors with that constraint that S is a constant. I'll just point out in passing too that if you did ask for the log score, then you can see that the construction of Grunwald and David gives you the usual exponential family as well. So that's the first comment. The second comment then is really about how we can generate scoring rules. And this just sort of elucidates the connection between proper scoring rules and entropy and information. This was shown in Knighting Raftery in 2007, that you can go both ways. So a proper scoring rule will imply entropy, and an entropy will also imply a scoring rule. And here's a nice little graphical picture of what happens if the parameter space is just 0 and 1. So obviously not very useful in practice, but this allows us at least to draw a picture. The concave functional there in the notation of the paper is negative I of p. And so the scoring rule actually is constructed by constructing a tangent to the point P. So here P is just the probability that theta is equal to 1. And where this tangent intersects theta equals 1 gives you the score if theta were 1. And where it intercepts where theta is 0 gives you the score if theta was 0. Okay, so that's the general picture. It's rather nice. And also from the two scores, you can actually then back out the black point there as well, the entropy function at the point P as the weighted sum of those two scores, or the expected score. In practice, in the cases we're looking at, for the case of second order local scoring rules, then that construction, which are harder to show, gives you this formula for the scoring rule. And now you can sort of see how those two constructions of the paper are linked together. The first term there are the Euler-Lagrange, well, it's the Euler-Lagrange components that will normally set to 0. And then you have the integral term. And with the choice of L in the paper, then that integral, the integrand just becomes proportional to P. And so the integral becomes proportional to a constant, which doesn't depend on P. And so you can see now that if you did set the Euler-Lagrange, satisfy the Euler-Lagrange equations, you're also just satisfying the S is equal to a constant. So they're linked together. I guess what I'm trying to say is that, actually the first point I want to make is so we can see in this context that solving the Euler-Lagrange equations is actually just saying we want to maximize the entropy. And so objective priors defined this way are actually going to be maximum entropy distributions. But the other comment more generally is that we can actually, seems to me, break away from the particular formulation of L that's given in the paper. And any L, as long as it gives us a concave functional for I of P, will generate a scoring rule that we could usefully use, it seems to me, to construct a prior. So that's, I guess, the main point. Finally, I just want to make an observation that we showed in our paper that I think, as Fabrizio said, if you do use a log score, then of course it's not invariant to reparameterization. But local scoring rules, without the log score included, actually are parameterization invariant. So that's something we showed in our paper in 2012. And then also, and it has to be this case, the entropy also becomes invariant, given the way it's linked to the scoring rule. So that's all the observations I wanted to make, but I just want to leave and finish up by saying congratulations again to the authors for such an interesting paper, and I'm looking forward to seeing how it plays out in the future. Thanks.
Thank you, Matt. The last discussion is by Federica Giumolé of University of Venice, Ca' Foscari of Venice, and Laura Ventura of University of Padova.
Thank you very much. Can you see my slides?
Yes.
Okay, perfect. So first of all, I'd like to thank Michele and Bayesian Analysis for organizing this event. And of course, I'd like to congratulate with the authors for their very nice work that gave rise to such an interesting discussion. My thoughts are joined with Laura Ventura. So in my discussion, I will consider 3 points. First of all, I'd like to talk a little bit about possible extensions of the proposed method. And then I'd like to comment on some important properties of the prior densities, in particular objectiveness and invariance. And then I would like to finish my discussion with a practical example, an application of the proposed method. So first of all, a summary slide, but well, the notation is the same as used by the authors in the paper. So the main points are, well, the starting point, which is setting a scoring rule equal to a constant. I think this is a very brilliant idea for defining an objective prior. In particular, the authors used a special mixture of the log score and the Iverinian scoring rule. But the first point is that I think that this idea could be generalized to different scoring rules. There are many of them. They may be used in different situations, and in particular, for instance, if we change the scoring rule into the Tsali scoring rule, we can obtain robustness properties for the prior density that could be useful in some settings. Or we could use many other scoring rules. In particular, I think that some of the commonly used scoring rules give rise to say trivial solutions for the prior if we put those scoring rules equal to a constant. But if we combine 2 scoring rules, or in particular 1 scoring rule with the Iverinian scoring rule, then we can obtain more interesting priors different from this one if we change the log score with a different scoring rule. I think that Iverinian scoring rule is quite important because it involves first and second derivatives of the prior. So it gives rise to non-trivial solutions for the non-constant priors in particular. Okay, so that was the first point. Then I'd like to say something about the properties of the resulting prior densities. As Fabrizio already said, the prior density, which is the solution of this particular equation, is proportional to the exponential of minus some function u. That's why I sometimes will call this prior a u prior. This function u is obtained by solving this differential equation. And the equation depends on the parameter c and also on an initial value. That could be, for instance, the value of the function u at 0. First property is I want to comment is objectiveness. The starting point is very objective in my opinion, but then the solution could be a prior which is actually very informative about the unknown parameter. It could be very concentrated on some particular regions in the parametric space, depending on the choice of these 2 parameters, C and U. So this is, I think, an important point that should be, that deserves further study, actually. Okay, so I was wondering if this is in contrast with an objective-based method, because again, the starting point is very nice, but the result then could be very subjective, actually. Okay, then, of course, I want to comment on invariance. Well, in some sense, I agree with the authors that invariance could be not so important, in particular in practical situations where it's difficult to find any prior for the parameter. But from the mathematical point of view, of course, it's a very important property. So I've tried to figure out how we can assess invariance starting from the scoring rule that we can use in this in the application of these ideas. I think that in order to obtain invariant prior densities, then the scoring rule that we use should satisfy this condition here, in the sense that if p theta is the prior that we obtain by setting s equal to a constant in the parameterization theta, then if we change the parameterization, the result by putting the scoring rule equal to a constant should be exactly the density that is the transform density of p theta in the new parameterization. So I've tried to see whether there are some scoring rules satisfying this condition, and well, unfortunately I couldn't find any, but well, some of the scoring rules that I've checked satisfy this condition just for particular transformations of the parameters that are linear transformations. But maybe it's not enough, but it's something. And this is also true for the scoring rule that the authors proposed. So for that mixture of the log score with the Iverinen scoring rule. So it is invariant with respect to changes of scale and location in the parameter. So I think it could be useful in particular, well, the idea could be fruitfully applied to scale and location models where the induced transformations in the parameter space are in fact linear transformations. Last thing I wanted to say is that I've tried to use these U priors, in particular 2 U priors suggested in the paper. I've tried to apply them to a particular example, which is inference on the concentration parameter for a directional model, which is the von Mises-Fischer density. So I've fixed the direction parameter mu, and the interest parameter is k, the concentration parameter. I've considered 4 different priors. First, the usual non-informative prior for k, then a prior that I've called G prior. This is obtained by, again, from scoring rules, but in a different way. And then I've considered 2 U priors with some specific values for the parameters U0 and C. These values were suggested in the paper by the authors, so that's why I've tried with those values here. And this is a plot of the different priors, and in particular, the green one is the first U prior, and the blue one is the second one. It's more evident from the green one. The support of this prior is limited to the interval 0, 1. So as I was saying before, this is very informative, in fact, about the unknown parameter. And it could lead to a misleading posterior when the value of the parameter is, for instance, very big, well, quite big, so that the support of the prior is really too short. So that there may be some problems on the tails of the priors, depending on the choice of the parameters. So this is an important choice, and I think that further suggestions are needed from the authors in order to choose these unknown parameters. Okay, so thank you very much for your attention.
Thank you, Federica, and thank you, Laura, for their discussion. And now it's the time to give the word back to the authors, to Cristiano Villa in particular for the rejoinder. I will then open, after the rejoinder, I will open the possibility for everybody else in the audience to ask questions. And this can be done either through the Q&A or at that point also by raising your hand and asking directly the question. The Q&A is preferred. We already had a couple of questions, but I will be happy, I'll be glad to see if anybody has questions, maybe to put it in the Q&A while Cristiano is speaking. Thank you.
Okay, thank you. I try to share my screen. Okay. Can you see the slides?
Yes, can you put them on full screen?
Is it okay?
Perfect, thanks.
Okay, let me start by thanking, obviously, Michele for organizing the webinar and giving us the opportunity to present our work, and also the many discussants that have gave us quite a few interesting comments, feedbacks, and suggestions. I'm going to run through a couple of examples that target some of the points of discussions, in particular invariance and the setting of the parameters C, U naught, and W. And I'm going to finish up with a few quick remarks. So about invariance, I think that the main argument that we made in the paper, and Stephen has stressed at the beginning, is that a prior should be chosen on the basis of how adequate it is for what he has been chosen to do. So in other words, even when you consider just one parameterization, so without taking into consideration reparameterization, you want to have a criteria that allows you to choose the prior because actually performs well in that particular scenario, rather than have some other properties like, for example, uniqueness. And as Stephen has already anticipated, there are many other Bayesian and even non-Bayesian procedures where invariance, or actually the lack of invariance, is present. Nevertheless, they are still employed. So let me do a very simple example. Let's assume we have a sampling distribution is an exponential, and we put a gamma 1, 1 on the parameter. We obtain a gamma posterior that has parameters 1 plus n and 1 plus n times the sample mean. And as Bayesian point estimate, we can take the posterior mean, which has the following form. Now, for some reason, let's say that we want to reparameterize. We are interested not any longer in theta, but in 1 over theta, say phi. And so we can easily transform the prior using, well, standard techniques, and we obtain an inverse gamma 1, 1, and the posterior again is going to be an inverse gamma with the same parameter values as the gamma posterior on theta. We look then again the point estimate, so the posterior mean, and it has the following form, so 1 plus n times x bar over n. And we clearly see here that the point estimate is not invariant under reparameterization. And in fact, we have the theta hat is not equal to 1 over phi hat. And obviously, this propagates in general also to the measure of uncertainty about your inferences, so in posterior credible intervals. And we can even go beyond that and consider, for example, the MLEs, maximum likelihood estimators, that they are invariant under reparameterization, but confidence in intervals not necessarily. Nevertheless, as we said, they're used. So furthermore, what we have done is to have a look on the same problem using an objective invariant prior, so Jeffreys prior. And what we obtain is the point estimates are 1 over x bar for theta hat and x times x bar over n minus 1 for phi hat. Again, even using an objective invariance prior, we have that the point estimates are not invariant under reparameterizations. So I guess that the key point here to take is maybe invariance may be a nice property to have in case that I don't know, I have already everything ready for theta and I'm interested in 1 over theta because it can save time in finding the prior and maybe proving that the posterior is proper. In the case of the prior, it is improper. But probably the prior has to be assessed on its adequacy to solve a problem rather than have this property. So it's more a nice property to have in many cases rather than a must property. So the second part, as I said, is about the choice of the constant C, you note, and it's not in the title of the slide, but also W, which is the constant that we use to weight the two components of information. And there are two major comments that have been made about these three constants. One is that the paper is a bit vague, if you want, in the instructions that we give in how this can be set up. And the second is that they may undermine the objectivity of the prior. So in the first case, yes, the paper gives some initial guidelines that obviously future research will need to address in trying to understand better for specific scenarios what are the best values that have to be given to C and or U naught and or W. And second, about as the choice of these parameters can bring in make the prior subjective. We need to consider that actually the way that these parameters act on the prior is on the shape. So they're not intended to bring into the density prior information about the unknown parameter like location or uncertainty and things like that. And just to show a couple of quick examples, because one of the critical issues that has been actually brought up in one of the discussions is about the tail of the distribution. And in fact, in a discussion paper, they say, well, let's assume that I sample 750 observations from a normal with 0 mean and variance 0.25, and I'm using a prior with the recommended settings, or one of the recommended settings, so C equal to 2, U naught 131, and W equal to 1. And they show that actually there are no issues. Now, the problem with that prior, it may be that the tail is very steep. It's very light, so it decreases to 0 pretty quickly. And in fact, they say, well, if I'm interested in estimating the precision, which is 4, the prior does not perform very well in inference. However, just by plugging in here, that's what I've done, U naught equal to 0.1, we've been able to produce a prior with a much heavier tail. And as you can see here is compared to the Jeffreys for the same problem, the inference that it makes on tau is appropriate. Okay, so yes, further indication on how to work with these parameters is a must, is required, but they should be able to obtain priors that can work in many or even virtually any kind of scenario. And another example here is that we have in the rejoinder is by controlling W, we can control the heaviness of the tail. Fabrizio has already shown something similar in the bounded parameter space minus m plus m, where choosing a particular W, he was able to have different tails in the prior, and here is what we have on a different parameter space of 0 plus infinity. So yes, the recommendation that we give in the paper tends to give priors with light tails, but these issues can be addressed. And to finish off, 3 comments and 3 remarks more than anything else. One is about no local prior. They've been mentioned by some discussant, because in certain scenarios like testing, they are preferable compared to other methods because they create this repulsion zone around the null hypothesis that allows to control the convergence rate of the base factor. Stephen has shown in a paper that actually the class of priors that we propose here has a subset non-local moments prior. So the prior that we propose actually includes many types of densities. Some are proper, some are improper, decreasing, non-decreasing, convex, non-convex, and even local and non-local. Second point is something very interesting and important. Yes, we can use different scoring rules, as it has been pointed out, and it's something that we have already started working on, to be honest. And yes, we started with the log scoring in Ibarinen for the reason that Stephen has explained at the beginning. But we are aware, obviously, that there are many other scoring rules that can be plugged in or can replace one or both of these scoring rules. So yes, that's a very good point and a very interesting area of research. And finally, this is more specific. It's something that interested me, that in spatial statistics, I was not aware of it. There is this matter correlation function that is used to capture the spatial dependence. And it looks like the practitioners have issues in implementing Jefferson reference priors. I believe because of the complexity in deriving particularly the reference and possibly checking that the posterior is proper, given that the prior will most likely be improper. And so they revert to using truncated uniform priors or log normal priors, where the discussant has implemented our prior for this specific problem successfully, because the implementation itself was pretty straightforward, and the resulting inferential outcome was in terms of performance, frequentist performance in the posterior, in terms of the mean square error, was better than what they're using currently, like uniform priors or log normal priors. And with this, thank you, I finished this short rejoinder.
Perfect, Cristiano. So we will continue now with asking the current attendees if they have any questions. So we have actually a couple of questions already presented in the Q&A that I would like to propose to your attention. I have sent a message to the question, to the people that ask this question. They want to actually ask them directly. In general, if you want to ask a question, you can probably raise your hand, I guess, in the webinar. And so I will give you the opportunity to talk. So the first question was received early after the presentation by the authors, and the question was, can we use this concept in deriving a prior with a range of variance that depends on the parameter, say, for example, a threshold parameter? I don't know if the question is clear. I will let the authors take the word in case.
Okay, maybe I'm going to direct the questions. I'm going to take the question and direct. Stephen, maybe you want to take this one.
I can, but I'm afraid you're going to have to repeat the question.
Okay, so the question is, can we use the concept that you have presented in deriving a prior where the range of variance depends on the parameter, for example, a threshold parameter?
You mean like a truncation or something? I'm not following the question, I think.
Let's see if the person that asked the question wants maybe to specify. I have an idea, but I'm not sure that that is the correct one. Del?
Maybe Michele, if the person can talk, so we can.
Yes, I'm actually allowing them to unmute themselves. Okay.
Hello.
Go ahead. Perfect.
Can you hear me?
Yes.
Yeah.
Yeah, say for example, you're considering a 3-parameter viable distribution or 3-parameter gamma distribution, where the third parameter is a threshold parameter. It is a minimum guarantee time parameter, say for example, and your variate x is greater than mu, the threshold.
So I mean, to me, that sounds like information you've got, right? And you want to use the information to construct a prior. Is that right? Have I got the right idea here?
Yeah, we have some sort of information in the form of minimum guarantee time.
So what you're talking about then is, can you combine objectivity in some part of the parameter space and subjectivity in another part? Is that fair?
Yeah, I don't know exactly.
That seems to be what you're suggesting. I mean, I guess we haven't explored that aspect, but off the top of my head, I wouldn't think that we couldn't pick out part of the parameter space to put our objective prior, and on the other parameter to put something that's subjective. I don't see why we couldn't do that.
Okay.
Perfect. Thank you very much. So we had also another consideration that Luca Larocca had presented in the Q&A. So I'm asking him to present it to everybody.
Hi, Michele. Can you hear me?
Perfect.
Okay, thank you. Well, I think that lack of equivariance under diffeomorphism of parameter space is a different thing from lack of invariance for Bayes estimates. Now, leaving aside our maybe different notions of what a statistical method, what properties a statistical method should or should not have, can we agree that they are two different things? And indeed, the lack of equivariance for Bayesian estimates is, let's say, perfectly legitimate because it depends on the choice of a loss function for that specific parameter. Thank you.
Not true, because both of those Bayes estimates arose from the quadratic loss.
Yes, but applied to different parameters. Apply to different things. I mean, if you think that you lose as a function of the parameter and your estimate, it corresponds to two different ways of modeling what you lose by being in error.
Now you've lost me. We're talking about invariance, and we're not doing a different procedure. We're doing the same procedure of quadratic loss.
I mean, square loss on variance is not square loss on precision.
Well, we know that. And that...
I'm sure you know, I mean...
Well, yes, but it's the same procedure. That's what we're talking about. What we're talking about is a procedure, that if I do my procedure on A and I do my procedure on B, I'm coherent. So we're doing exactly the same procedure on a different parameterization, and we get a different answer.
Okay, thank you. I still think that, I mean, you are doing this much earlier in the process because you are doing this to produce a prior and then from that a whole Bayesian posterior. Whereas, I mean, the estimates as a point estimate is really the last step when you want to summarize the distribution with a single number.
Why would that matter? The point is that why the focus on the prior? Why not also focus on other procedures that lack invariance, which are commonly used? It seems as though the arguments are sort of directed at the construction of priors and little attention on other procedures.
Well, okay, I see your point, but I'm sort of unconvinced. Well, thank you for your attention.
Perfect, thank you, Luca. Let's see if there is anybody else who wants to provide their perspective or ask questions, clarifications. I believe you can raise your, the attendees can raise their hands, right? Okay, I don't see any raised hand. On the other hand, yeah, it's almost 1 hour and 40 minutes past the moment we started. I definitely think that this was a lot of food for thinking, and definitely these discussions serve the purpose to present the paper and provide conflicting and different point of view. So that's exactly the point of the discussion paper, to stimulate conversation. And I'm particularly glad that we've been able to actually have a discussion that involves the objective-based community. And again, as previously mentioned, vision analysis is very open to get papers from the objective-based community. And we also have are very much interested, right, in getting discussion papers. When you submit your papers, you have an option always to propose your paper for discussion. So please use that option if you think that your paper could provide an interesting conversation to the community. We are organizing the next discussion paper for March. I will send out actually an announcement later today to the ISBA mailing list, so stay tuned. And I thank you for now. I thank the authors and I thank the discussants. I thank the attendees for participating to this webinar.
Thank you to everyone.
Thank you.
Thank you.
Thank you.
Many
Thank
thanks.
you. Bye.
Bye bye.
Thanks a lot, Michaela. Thank you.
Thank you.
Thank you.